In this video, we're going to derive something known as the geopotential height. Firstly, let's think about coordinates. We define two horizontal coordinates to lie within the surfaces of constant geopotential. Then we define our vertical coordinate to increase in the direction of grad phi and to be zero at the geoid, where the geoid is the shape of the oceans under the influence of gravity and rotation alone. So that's our mean sea level pressure, or our mean sea level rather. So we'll add an arbitrary constant to all the geopotentials to make the value at the geoid equal to 0, shown there as phi of z equals 0 to be 0. So consequently, the geopotential at a point x is now the work done to move a unit mass from that geoid to that height. So if the work done is phi of x minus phi of 0 at the geoid, and phi of 0 is 0, then the work done is simply phi of x. The magnitude of the apparent gravitational acceleration, Ga, is the magnitude of the gradient in the geopotential. And for atmospheric science applications, this may be approximated as the following formula, where the apparent gravity is a function both of the latitude and a weak function of height. And for most meteorological uses, we'll actually ignore the functionality of height. The previous relationship shows us, as I've said, that the geopotential is a slight function of latitude, and that's shown schematically in a rather exaggerated depiction. So imagine moving along z equals constant surface. As you move from low latitudes to high latitudes, you encounter larger and larger values of the geopotential. At the geoid, z equals 0, and so Ga of phi and z is just a function of latitude. So you can see that gravity is a minimum at the equator and a maximum at the poles. Now, why is that? Think back to how we derived apparent gravity. At the equator, the ordinary Newtonian gravity is inward along the local normal, but the centrifugal force is outwards and directly opposes gravity. Whereas at the poles, gravity is downwards, but the centrifugal force is at right angles, so they don't oppose. Now, which latitude has Ga is equal to 9.80665, which is the constant at the front of the equation? If you guessed 45 degrees, then you guessed correctly. Now, integrating the equation we had earlier, we see that the approximate geopotential for small z is the equation there. Phi is equal to Ga by z, because the dependency upon z is very weak. So consequently, we can work out the height of our geopotential surfaces. Here's our approximate geopotential again. So what is the value of geopotential at the South Pole? What is the height of the geopotential surface with this value of geopotential at the equator? Well, we can define something known as the geopotential height, which is a scaled version of the geopotential that very closely matches the real geometric height, but is not exactly the same. So if we divide through the geopotential by 9.80665, which is gravity at 45 degrees, this is approximately Ga multiplied by z divided by 9.80665, you get the geopotential height. If you take the geopotential and you divide through by gravity for that given latitude, then you obtain the geometric height. So the geopotential height and the geometric height will be similar, but won't be precisely the same. And that's shown here. So consider a geometric height of 1 kilometre or 1,000 metres. At the equator, that height will be 998 metres, and at the poles it will be 1,003. And likewise, as we move up, for larger and larger geometric heights, the difference between the geopotential height at the equator and the pole will become larger.